The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Today we're going to do sort of the second part of our discussion on walking. I want to start with what sounds like a little bit of a remedial question in some ways in numerical analysis of these walking gaits, because it forces us to be more careful about talking about the dynamics through collisions and on Poincare maps. Okay, so I actually want to start the discussion by just asking, given we've defined a walking robot with some stance dynamics and some sort of collision dynamics like we did for the rimless wheel and the compass gate, and the need compass gate quickly, I just want to ask the simple question, can you find the stable limit cycles, or even any periodic gates of the system? Okay. So the first question I want to find equilibrium fixed points of the Poincare map. Okay, so remember we talked about the Poincare analysis of limit cycle behaviors last time, and we said that this continuous time stable oscillation could be nicely characterized as a discrete time fixed point analysis if we're able to, for instance, for the van der Pol oscillator, right? I called it X and X dot on the van der Pol oscillator. If we're able to design some surface of section and just look at the state of the system every time it goes through that surface of section, right? Then I can build a Poincare map, which is on the Poincare, I've got a state X, which is just some potentially nonlinear mapping from the nth crossing of this map to the n plus 1th crossing of the map, yeah, of the surface of section. So given I have some sort of bisecting surface here, what I'd like to do is now find the fixed points of that solution, right? Which means xp star is just p of x p star. Yeah, simple enough. And that should tell me where I've got a fixed point, and therefore where I have a limit cycle. It doesn't actually imply necessarily that that limit cycle is stable. If it was stable, then you could imagine finding the fixed point, for instance, of the van der Pol oscillator just by simulating the van der Pol oscillator for enough time, right? It'll eventually go and do the work for you and find its way to the stable fixed point, so if you just run it long enough. But if it's unstable, that's not as easy to do. And for systems like the compass gate, it turns out the basin of attraction is sort of small enough that you could spend a long time trying to find initial conditions which happen to simulate their way into the stable fixed point. Okay, so we want to do better, get some better tools. Given what we've talked about in other parts of the class, if you wanted to find the roots of this, the fixed points of this system, how would you do it? I just slipped a little bit and gave you half the answer there. How would you do it? I've got some big complicated function p. I want to find the fixed points. Close, right? So I want to find the roots of some function of xp, right? So it's equivalent to finding the roots the roots of, pxp star minus xp star. Right, so if I can evaluate p through simulation or whatever, then I can evaluate this, and I could just hand it to MATLAB or something and say, find me the roots of this nonlinear function. Okay, and that's easy enough. We talked about the Newton method for finding roots we talked about the constraint solvers that SNOPT and the like uses. Okay, so in fact we could just hand it to SNOPT as is and ask it to do its thing, and it would do numerical derivatives and it would find its way to some zero of that function. We're going to be in a lot better shape though if we can compute the gradients of that analytically and hand it to SNOPT. It'll take a lot fewer trials. And I want to sort of do that exercise quickly, computing the gradients of the Poincare map, because it's going to be broadly useful in control and because it forces us to really think about how we define that Poincare map. Okay? So what we'd like to do, let me just say, it's easier if we have partial p, partial x available for the optimization, right? Okay, just think ahead for a second here. How would you compute if I would just ask you off on the street, I've got a Poincare map, how would I compute the gradients? What would you think? What would you start trying to do? Yeah. So where have we analyzed the perturbations before? What kind of tools go with that idea?
Well, if we linearize about a point.
Yeah, so again, around any given point, which defines a trajectory, we could do backprop through time if we cared about a cost function. But remember, the trick behind backprop through time, computing those gradients, the reason that was so efficient was because we were trying to find the gradients with respect to a scalar output. So backprop through time did a forward pass and then connected it to that scalar cost function output and then backed up a minimal state vector. The forward version we talked about was just computing the gradients marching forward. I called that real-time recurrent learning, RTRL. And that's actually sort of 80% of what you need to compute the gradients here. Is there something I did wrong? Yeah? No? Okay. So RTRL, which we've talked about before, and I'll say again real quickly here, is a lot of the answer, but there's a subtlety that I want you to see. Okay. So let's be a little careful about how we go from xp of n over to xp n plus 1. Right? That mapping is sort of a complicated. There's a transition from this discrete time system to the continuous time dynamics, a simulation of those continuous time dynamics, potentially an impact map at the end. We talked about the rimless wheel doing the Poincare map right at the impact. So let's do that carefully. So let me say that, let me define xp at n as being equivalent to, in continuous time, x, the original vector, right? I use a p to denote the discrete time Poincare thing, at the time of collision of the nth collision, right? In the walking case, we always did our Poincare map at the same time as the collision. Yeah. More generally, you could just think of this as sort of a collision with the surface of section. Okay. In the walking case, because the collision has some dynamics, we want to be explicit about whether it's before or after those dynamics, before or after the collision. Right? So I'm going to say, I'm going to call our discrete time state of our system to be the state of the system immediately after I process that collision dynamic. So I'm going to put a plus there. Minus would be just before the collision. Yeah, they're both at the same time, but there's an instantaneous dynamics. Okay, so I have this. I know how to go from xp to a continuous time thing. And then I know how to go from this to march that forward, right? If I know when the next collision is, then I know that had better just be x of tc plus n plus the integral from 0 to tc, well, sorry, from tc plus n to cc minus n plus 1 of, let's just say my dynamics are x dot equals f of x. I'll forget about control for a second just to keep it simpler. That. Right? Once I go from my discrete time thing to a continuous time thing, I just integrate my equations of motion forward until I collide with the surface of section again, right? And I want Tc defined somehow. I want to somehow define that surface of section. And to define that surface of section, and that collision time, I'm going to define or more generally a collision, yeah, as some function that equals 0. Right, there's some manifold of states that I can describe by this function, which will define my surface of section. Yeah. So what was it for the van der Pol oscillator? I defined my surface of section to be this thing going forward. So what this surface of section is, you define it as some function which just happens to be 0 here, right? So a perfectly good candidate would be like the distance, the signed distance, let's say, between here, between your current state and that manifold. You okay with that? I don't think I said that very well, but if I want to define my surface of section, just define a function of state, which is non-zero everywhere and 0 where the surface I care about is, yeah? And that's going to allow me, as you'll see, to do things like taking the gradient of knowing when I'm going to collide with that surface of section. So this could just be, for instance, the signed distance between, let's say, the foot of the robot and the ground. Yeah? So when the robot's foot hits the ground, that thing's going to be 0. Yeah? When it's below the ground, it'll be some negative distance. When it's above the ground, it'll be some positive distance. Okay? And that's going to allow me then to define this at a time of collision. This thing had better be 0.
Is that also going to include the negative x dot axis though?
Good. So I'd want to define it in a way that doesn't include that, right? So I could put a so the robot's foot colliding with the ground doesn't have that problem if you think about it. But I do typically put something like a velocity term in it. Let me just write down what I use for the rimless wheel. Actually, I've got it here. So I do phi of x is just the sine function of theta dot times theta minus gamma minus alpha. So if you don't remember all those symbols, that's almost useless. But this is saying the sine of theta dot tells me if the robot's moving forward, yeah, then I'm going to look for the collision with the ground at this angle. And if the robot's looking backwards, I'm going to actually look at the collision with the ground at that angle. And that's how I end up getting the surface of section, which doesn't go, just goes in the top half of the and bottom half of the thing. Yeah. So you can define whatever function, but you just want it to be not 0 here, right? Okay, we're getting closer to having this thing be well defined. In fact, this is a very common way to define a collision in any hybrid system. So systems that are continuous with discrete impacts are called hybrid systems. Yeah. If you wanted to simulate a hybrid system in MATLAB with ODE, then you would very much do that by defining a function, which they call a collision function, or a collision event function, which has got zeros here. And you can hand as your options to the ODE solvers in MATLAB event functions like this. And they will very carefully watch for a crossing of that event function across 0, and pinpoint the time and state at which that thing goes across 0. So this is a very common notation in hybrid systems kind of worlds. Turns out if we do care about finding this gradient of the Poincare map, then this is going to also be the enabling thing which allows us to compute that gradient. Okay, so we have this x of t minus. We've gone from just after a collision. We've integrated forward over our continuous dynamics. Yeah. And then, so now we're at the time of the new collision, tc minus n plus 1. We're going to compute the new dynamics by having some collision function. In the rimless wheel, it was just the thing that took out some energy because of the inelastic collision with the ground. So the final piece of the puzzle here is x of p n plus 1, which is equivalent to x of t c plus n plus 1, which is some impact dynamics. I'll just call it big F of x of t c minus n plus 1. In 90% of the cases that I would care about, it's only a function of x. I like to write in the more general form in case you have things like moving obstacles, let's say. Right, in the surface of section case for limit cycles, I think it'd be pretty unusual to have a direct dependence on time. But it doesn't make our derivation any more complicated than if you wanted to worry about, collisions with moving things or something like that, you could do that. Okay, so this is a sufficient recipe now for simulating the Poincare map, right? If I want to just evaluate in the simulation with the Poincare map, someone says I'm at state xp on the nth Poincare map. I'm going to turn that into my continuous time thing. I'm going to integrate forward my dynamics just like we always do, but I'm going to stop at a particular time, tc minus, which is defined as the time when it causes phi to equal 0. Yeah. And then at that time, in the case of the walking robots or any collisions, physical collisions, you might have to implement the discrete collision dynamics. And that takes you back to the next map. Right? Good. So how do we take the gradients of that? It's almost trivial. Almost trivial, right? We know how to take the gradients of this, right? We'll do it again just in one line, but we know how to just integrate forward the gradient dynamics, like to compute the long-term gradients of x. The only subtlety is that When I'm computing the gradient, I'm changing xp a little bit. I'm trying to do a sensitivity analysis between xp. If I change xp a little bit, how's it going to change xp n plus 1, right? So the only subtlety is that when I change xp a little bit, it can change my collision time. Yeah? So you have to make darn sure when you're taking the gradients that you capture the changes in collision time that are due to your change in initial conditions. Other than that, it's almost exactly the RTRL code that we had done before. Okay? And that turns out to be not so bad, so I want to do it. All right, so we can just go forward with the chain rule here. So xp of n plus 1 dxp of n. Well, that's going to be, first of all, the gradient of this f, right? Partial capital F, partial x, and then times the gradient of the inside. Okay, the inside is defined by x at a certain time, so this is where that comes in. First of all, let me say we're doing this linearization around some nominal trajectory, right? We have some xp naught that we're linearizing around. That implies we have an xt trajectory that we're linearizing around, which I'm calling x naught. Yeah. And it implies that there's some nominal time of impact time of collision that we're linearizing around, which I'm calling tc naught. Okay. So the obvious gradient here, partial f, partial x, gets us backwards past the impact dynamics, and then we have to figure out what the state of x is relative to the initial conditions at time evaluated at the original impact time. Right? And then the subtlety is that I can also increment or decrement the index of the integral, the limits of the integral, which has the effect of, well, adding this term again, modified by that increment in the limit of the integral. So I get f of x times that increment. Okay? So let's do this in a picture, right? So let's say I have some some manifold defined by phi equals 0. And I have some nominal trajectory that I took to get there. I got to my switching surface. I'm calling this x0 of t, yeah? And this one here is x0 of tc0 plus n, to be entirely confusing, I guess, or just a lot to write. I could write that equally well as xp n naught, right? And what I'm trying to figure out is what's the state going to be if I'm going to simulate my system from slightly different initial conditions when it hits the map, right? So using my multicolored approach here, if I take some increment in x0, right? And I simulate my new dynamics forward, then maybe I get something pretty similar. But at time, but my original end of time, if I evaluated this integral for the same amount of time, there's no reason to expect I would get back to that switching surface, right? So this is my modified thing at Tc naught. But what I would figure out is where it's going to be the next time it hits the surface. Bless you. So you can do that by figuring out what this difference is. This is partial x of t given the initial conditions at time Tc naught. That's this term here, corresponds to this. Yeah? But I'd better also add in the dynamics of this thing pushed forward by the amount of time necessary to get me back to the surface for that collision. Yeah?
So you never take a derivative of the phi function?
You do. I'll show you. So in order to get this, we're going to have to take a derivative of the phi function. I can't tell people if people are bored by this or intrigued by this or don't care. But, okay, does that make sense? Good. All right, so how do we figure out the change, the increment in time given the initial conditions? Well, it's defined based on that phi equaling 0 is the thing that defines this collision surface, so it's going to be used in computing that increment in time. Okay. So if phi equals 0, then it better also be the case that d phi dx p n. Let me just write this. I'm sorry. Tc minus or Tc n plus 1 here. X of Tc minus n plus 1, right? This is just the derivative of that thing based on the changes in xp. I've defined that. I'm saying that even though I changed xp, phi had better still be 0, right? I'm integrating until I hit that surface. So this thing had better equal 0. And I can take that derivative with partial phi tx partial x t evaluated those same places. Okay, I'll save myself from writing that last equation, but obviously I can now solve this for dtc dxp. Yeah? Stepping back just a second, so I'm making an increment here. I'm defining it that even though I made that increment, I still better get to phi equals 0, right? I can look at the change in phi that could potentially occur. It's going to also depend on the change in x and the change in final time, right? And that allows me to solve for the final time that must have made that happen. Must have made it so I get back to the switching surface. Yeah? Okay. That's really the only thing you need to know to make all of your tools that we've used for open loop optimal control, for instance, for the Acrobat and the cart pole, work for the walking systems. Yeah? The additional advantage of thinking about this now as on the Poincare map, is we can actually, in some ways, we can do even easier control. Okay. So what did I just solve for? I solved for partial p partial x.
Pause for a second.
Absolutely, yeah, please.
I'm trying to get my head around all this.
Yeah, good. I want questions.
So we started from there. We said, okay, we have a Poincare map, and then we define the surface as phi. And that f is the integral of that small f.
No, not necessarily. I mean this to say, so it happens that oftentimes at the surface of section we want to compute a discrete collision dynamics, right? Which is just some other function, which I'm calling capital F. I don't mean that to be directly related to that. I can see that coming right after the integral, that's confusing. You want to call that something different? We could call that something different. Yeah.
So it's different.
Yeah, this is the equation which says, well, in the rimless wheel example, it actually says I'm going to change coordinate systems back to where my new leg is on the ground. So I'm actually going to do a discrete change in theta, and I'm going to take away some of the theta dot because I've lost some energy into the ground, right? And in general, when you have collisions in mechanical systems, if you model them as impulses, you're going to have some function like f. Okay.
That's n plus 1 or n plus, right?
Sorry.
Okay. Then we took the drill xp n plus 1 to xpn. I want to see.
This is equivalent, right, to being the partial p partial x. Everybody sees that?
Yes.
Yeah?
Yeah.
Okay.
So we want to see if we a little bit change on this phi, then how much the next point that we reach the change, right?
Not a little bit of change of phi. What we're changing, the thing we're changing is xp.
Yeah, the point that we start on phi, if
Yep.
we change it a little bit on phi, then where the next point would end up.
Yes.
And x naught and all the knots are basically the initial trajectory we would have taken
Yep.
without changing.
Because we're doing everything as an increment, right? We're doing an incremental analysis. I want to say that the new TC is going to be some, TC0 plus this increment, yeah?
And so we know that the phi, because we defined that phi should be 0. It's
Yep.
phi of t and x.
Yep.
And why the derivative of this with respect to xp should be 0? xpn.
I've defined the problem that way again, right? So I said, so even if I make a small change in xp, I still want it to be that in my new collision point, I'm not going to call it a collision point until phi equals 0.
Right.
And if phi is going to equal 0 along everything, then certainly equals 0 on an increment in xp, yeah? Yeah? So it's tempting to say, so we got, we've got gradient-based calculations flying around here. We've been doing a lot with that. I think they're pretty powerful. It's tempting to say that if I have a discontinuity, then it breaks all my gradient calculations. It doesn't break them, you just have to be more careful about them, yeah? Okay, so we can take a gradient through the impact of a walking robot, no problem. You just have to use this, okay? This will be the same if you're doing a, ping pong robot or something like that, right? Anything with collisions, a mobile robot that runs into museum visitors or something like this would also have an impact map. Okay, so that's all you need to use all those methods we did before. Okay. So if I wanted to now optimize the trajectory, let's say, of my periodic system, right? If I had my dynamics, now we're back. I did this just in the simple case of f of x, but if I had f of x comma u, and I wanted to optimize u in order to do something good on the Poincare map, minimize some cost function, I can take the gradients, I can do my optimization, right? But this idea of actually changing to a discrete time system is a bit empowering too. You can always do it. It's not that you only do it for walking robots. I could take any continuous time system, instead of looking at it at every t, I could look at it, at discrete intervals of time. Right? I could take a ball that I throw across the room. It has no impacts whatsoever. Well, at the beginning, and then right, and I could look at the system at x of time 0, then at t equals 1 second, x of t equals 2 seconds, and I could build a discrete time system from any of these continuous time systems. It's particularly nice to do it on these walking robots because, well, let's do it. So what have I just done? Right, I've computed partial p partial x, which is telling me that I'm approximating, it's a Taylor expansion, right, of my dynamics around some nominal point, yeah? If x nominal is a fixed point, yeah, or if I just change my coordinate systems to x bar is xn minus x nominal n, right? I could do the time varying thing if I want, or I could just do it simply if x bar not is a fixed point, then I'm left with a model like this, right? Careful here, p's everywhere. P n plus 1 is a x bar p of n. Okay. I can immediately look for the stability of that model by taking the eigenvectors, right? Eigenvalues. Stability conditions are in discrete time, so those eigenvalues had better be bounded by 1 and -1. It's not the same condition, but perfectly easy to analyze the stability of the fixed points. Right? So now for if I just cared about analyzing a passive walker, I've immediately found, I've got ways now, by computing partial p partial x, handing it to SNOPT or something to find the roots. I can find the fixed points, and it also happens that by computing partial p partial x, I can evaluate the stability of those fixed points. Yeah. The rimless wheels fixed points, if you remember, there was 2 of them. One was a rolling fixed point. One was a standing still fixed point. Both of them are locally stable. The compass gate, if you remember the compass gate, it also can have multiple fixed points. It has one fixed point for a nominal slope. It has one fixed point that's walking. And it actually has an unstable fixed point. Now the cool thing is, so Ambarish Goswami, who's a friend, did a lot of the initial compass gate analysis. If you start inclining the ramp steeper and steeper, then those fixed points change as a function of the dynamics. something really interesting happens. It's not surprising that these are complicated dynamics, but you actually, at some point, at some critical angle, you get a period doubling bifurcation. So you get an extra fixed point that corresponds not to a one-step fixed point, but to a two-step fixed point. So what does that mean? What does that correspond to physically? What is a two-step? What do I even mean by two-step on the Poincare map?
It's like in between two different points.
Right. So at x of n plus 2 is going to equal x of n, but at x of n plus 1 doesn't necessarily. But every other thing is going to be the same. So what does that physically correspond to in the walking? It's more of a limp, I'd say. Yeah? It's some asymmetric gait. It's like this. These robots start doing, potentially asymmetric thing. Every other footstep ends up landing in the same place, but not every footstep. Okay? So it's actually, there's a lot of interesting work just looking at these passive models and just looking at the stability of these passive gaits. Okay? I do want to make one note here. If you're looking at the eigenvalues of A, the way I've defined it, so the trivial condition here is that the eigenvalues of A had better be less than, the magnitude had better be less than 1. There's different notations for working on the Poincare maps. My notation is to denote x of p, where x is the same size as the original vector, right? Because that's more useful in simulation, that's more useful in most of our computations. But remember, the Poincare map effectively reduces dimensionality by 1. And if you just, in the way I've written it here, if you just look at A that comes out of a stable periodic oscillation, there's actually, the way I've done it, there's always a trivial eigenvalue of 1, which doesn't degrade the stability of the system. What does that eigenvalue correspond to? Yeah? If I take my stable rimless wheel, I compute A, I take the eigenvalues, I see that the system's stable, it goes to my nominal thing. This is the standard stability criteria for discrete time system. But I notice that there's actually always a trivial, there's a one eigenvalue that equals 1.
It makes sense because it's in a loop. So.
Good, right? Do people see that? There's one direction that I can push it in which it does not reject that disturbance. Right? And that's the direction if you push it along the limit cycle. Right? So there's two ways to do it. I'm sorry to make it complicated, but there's 2 ways to do it. If I were to have redefined my coordinate system on the map, I wouldn't want to call it x anymore, but something that reduced the dimensionality of the map by 1. Right? And then I could use this condition alone. But in the way I've done it, and in the notes and in life, I like to keep this sort of as the same dimension of x. And then because I want limit cycle stability, it's absolutely the case that one of the eigenvalues, there is a direction in which those disturbances are not rejected. That's what I want. Yeah? Okay. So the way I describe it in the notes is that what you want for stability of the periodic gate is you ignore the first eigenvalue of 1. The rest of them better be. I want it to be only one direction that doesn't reject disturbances. You with me? Okay.
What happens if you have 2 dimensions? 2 lambdas equals 1.
Yeah. Then there's some other direction that doesn't reject disturbances, and then I start questioning whether it's stable. Right? I wouldn't call it stable in the sense of a limit cycle stability. Right? If I could push, in some other direction in state space and doesn't get rejected, then it's not going to return to that orbit. Right? It's just there's a special direction along the orbit which I'm allowed to push, and that's what defines limit cycle stability, right? But there's only one direction.
What if you have this limit cycle in 2 dimensions?
Even in a high dimensional space, right? I have a 50-dimensional robot going around. There's only one place that trajectory is going forward that I'm allowed to push and not reject the disturbance. Every other one better converge. Yeah? For me to call it stable. Okay, we did the case for the non-controlled system, but we're only a stone's throw away from doing the actuated version. I'm not going to write it out again, but let's say let's do it a little. Let me do it a little carefully, just to say what I mean carefully. So if I want to do the controlled case, we get back to a system like this. We talked about in the policy gradient, in the policy search world, that I could then define U to be a tape of U's, or to come out of a linear feedback controller, or whatever sort of parameterization. But I like to think of it as being some function which depends on a parameter vector alpha, and could generally depend on x and u. Right? So there's a different way to think about control in the discrete time Poincaré sense. One way to think about it is, let's say every time I hit a surface of section, or my foot hits the ground in the walking case, yeah? Why don't I change the parameter vector alpha? Okay? But I'm going to make decisions only once per step. And then I'm going to execute this policy for the duration of that cycle. And then the next time my foot hits the ground, I'll make a different decision about alpha. You can imagine, so let's say that pi of alpha on my compass gate walker, and we'll use this example in a simulation in a second. Let's say I have a controller that runs during the limit cycle, which tries to set my interleg angle to be some desired value. Okay? Every step I take, the only decision I make is what should that desired interleg angle be for my compass gate. But over the course of the cycle, I'll simulate a PD controller that tries to make that interleg angle happen. Yeah? But my discrete time decisions are just what interleg angle should I be. Fumia's got a compass gate that works with open loop trajectories that play out, where his major parameters are the frequency and phase of the periodic input. It's amazingly stable coming out. It's like a beautiful example of open loop stability. Okay. So Fumia and I have been talking about changing the parameters of his open loop controller once per step in order to try to regulate the behavior of the system. Okay. There's lots of ways you could do it. But generally, what that gives you, if you just try to compute these exact same gradients again, we've computed the gradient with respect to the initial state, but we could also compute a gradient with respect to alpha. And what that could give me here is a model like this. Yeah? I'll call it B because I'm thinking of alpha like a control decision, yeah? Where alpha bar of n is the difference between my control decision at n minus whatever the nominal alpha is. Let's say. Okay, so let's say I find a stable limit cycle where I just command the inner leg angle to be, I don't know, pi over 4 every step. And I can find a stable limit cycle behavior. Well, then if someone pushes my robot, computing these A and B matrices give me a nice, simple way to make discrete decisions to try to stabilize that robot. If away from my limit cycle, I can correct for those differences by just saying, okay, next time take a bigger step, or then take a smaller step, right? And how would I design that rule to change alpha? How would you design it if you wanted to make a feedback law on alpha here? This is a discrete time linear system. I could just hand it to MATLAB and call LQR, discrete time LQR. It's DLQR. Give it A, B, Q, and R. It'll give me back a negative K alpha, Kx that defines alpha, right? You with me on that? So the discrete time summarization of the dynamics in this way can actually make it very natural and very simple to compute controllers which stabilize a walking cycle, for instance, where you make decisions once per step. I want to show you some work that Katie Bill did in my lab, where she did it on the nonlinear case for the compass gate. She, instead of linearizing this, she went right with the full nonlinear Poincare map, right? She just did x of n plus 1 is some Poincare map of x of n times alpha, parameterized by alpha, yeah, or alpha n, let's say. And the compass gate, how many dimensions was it? It's 4 basic dimensions. There's 2 angles and 2 velocities. Okay. And it's just about the right size that you can try discretizing and doing value iteration, right? So Katie had some nice work showing that on the compass gate we can really get a pretty good sense of the nonlinear optimal solution by just popping this discrete time control problem into value iteration, doing some work, and computing back an optimal feedback policy which tells you where you should step every time in order to stabilize your gate. One better, if you add one more dimension to your compass gate robot, you can actually think about where it is on terrain and make it walk over rough terrain. So maybe I didn't spend enough time in these 2 lectures convincing you that nobody knows how to make robots walk on rough terrain, but shoot, it's going to take a second here. But you might know for yourself that you don't see a lot of walking robots walking on rough terrain yet. Big Dog's sort of the exception. Big Dog seems to be pretty good. We've got a little dog upstairs in our lab, which is also pretty good, I think. They're different. Little dogs can see the terrain and Big Dog can't. So we're supposed to be doing the long-term planning of, for the long-term research for Big Dog, is the idea. Now we've had that entry music here. It's a very dramatic simulation that follows. Okay, here's Katie's work on the compass gates on rough terrain. Yeah. Little compass gate robot. It's making control decisions every footstep. It knows where the terrain is. Popped it into a big value iteration solver. And this thing can walk over almost anything, right? It actually does, it applies a torque at the hip with the PD controller I described, and it also puts in an impulse at the foot one time every post impact, so it can push itself forward a little bit. Well, this thing is pretty good, right? And it's just converting this sort of complicated looking problem into a value iteration problem.
Does it have like the exact terrain?
It does, yeah.
The slope of the terrain?
It doesn't think about the slope of the terrain. It could. But the reason it's tractable, actually, if you can tell by the foot points, it wraps around. So we've got a limited state space in X.
Doesn't worry about the swing foot hitting the ground?
We ignore, if you look real carefully, I think the leg gets a little shorter every time it goes, right? But it's a massless leg, but there's no dynamics like that. We built the robot the same way. We have a little twig toe that pulls up, yeah?
How do you find impulse at the foot that's lifting up?
It's trivial in simulation, yeah? How do we do it in real life? Not as well as we'd like, right? I mean, Fumia's got a design that's got a servo that pushes as fast as we can. We talked about, pneumatics that would be a little faster, but we haven't run that yet.
Do you need the foot impulse to be able to?
It's interesting. So she actually did the case of just hip, just foot. They both work. They both stabilize the walking on moderate terrain, but together they're much more stable than the other. The thing that the hip one always gets in these configurations where it goes, whoa, like this and falls backwards, right? You need a little bit of foot energy to get over. And the one that pushes off with the toe keeps putting its foot down in the wrong place, roughly, right? There's one thing that Katie's simulations had problems with. The guys in my lab know. But there's a pretty sort of very visual, I should find the video maybe, but there's a very visual thing that we had problems with. What was the problem I always talked about with value iteration? Even if you could tile the space, you got to watch out for something. Yeah, there's, your discretization. If there's hard discontinuities, you can do things wrong in your discretization, right? Your discretization can be a poor approximation of your continuous thing. So Katie simulated a bunch of terrain that had holes in it, like cliffs, and had these beautiful policies that would, choose their step across, Karate Kid sort of style terrain. But every once in a while, the mesh points would land in the wrong place, and the stupid thing would put its foot right in the middle of the hole, right down into the ether, yeah? It was sort of the textbook case of value iteration resolution problems. Okay, so walking isn't any harder than any other robot, really. There's mechanical challenges. You have to carry your actuators. You're typically dealing with actuator saturations a lot. It's definitely underactuated, right? I don't mean to say it's easy, because I think the Acrobat's sort of rich and hard, but it's not significantly harder than the Acrobat. And this is, remember, the Acrobat dynamics. The only two differences are that you have to worry about, you tend to think about Poincare maps to define stability, and you have to worry about these collision dynamics. Mm-hmm. You get 100 degree of freedom. I'm not showing you a 100 degree of freedom robot here walking along. But you could. I mean, we're getting there, right? So the Dirk-Hall type methods that we're using with the LTV linearization, we think that's going to work pretty nicely for Little Dog, and that's 36 dimensional, walking on very rough terrain. So there's been a lot of work in the control of this sort of outside the optimal control view of the world. I'd be doing you a disservice if I didn't tell you about a little bit of it. Make sure I said everything I wanted to say here. Okay, good. There was one other point I wanted to make. There's something you can do in discrete time that you can't really do in continuous time when it comes to stabilizing controllers. If anybody get it from just that? I said it very obtusely, but yeah. Yeah, good, right? So if in discrete time, I can actually find an action, potentially, it depends on B, right? I could find an action which would actually drive me to 0 in my error dynamics in a single step. Right? In continuous time, getting there arbitrarily fast means setting your gains arbitrarily high. In discrete time, that's not the case. I can set a finite magnitude gain that will get me to 0 in a single step. Right? So that's called deadbeat control. It's a very beautiful goal to have for a walking robot. Okay? If I get perturbed by the terrain or by someone hitting me with a baseball bat or whatever. You should see the videos that the robotics people make of walking robots. Then a very beautiful goal is to say that before my next foot hits the ground, I'm going to cancel out all the error from my disturbance. Yeah. Certainly you can do that here if you have no limits on alpha, and if B is full row rank, then it's just an algebraic equation to compute what alpha n had better be. Yeah. I could just say, compute something that I could basically, it's like feedback linearization. I could just cancel that out. Yeah. Sometimes you can't do it, but I want you to know that it's a beautiful goal for control. We'll see in the running bit, we'll see some running models where you can do deadbeat control. The compass gate, if you had the right parameterization, you could do compass gate control. John and I were debating this last night. I don't think that the PD controller is probably going to be enough to give you deadbeat control, because it won't simultaneously take out your energy and get your foot in the right place. But it's possible we could actually do the analysis and ask that question, answer that question. Okay, so thinking about these things as discrete time control problems is pretty beautiful. More generally, though, we can do control through the swing phase in this case, or between the surfaces of section in a general limit cycle case. Yeah, and if you want to do that, you could do a shooting method. You could do dir call, optimize some trajectory. You have to be careful because the time can change during your optimization, the duration of your trajectory, but you could do that. And then optimize it. But just like we showed in the acrobat and cart pole case, people have come up with more, I don't want to say problem specific, but more sort of problem specific solutions. Yeah? So Ambarish Goswami did some nice work. Can anybody guess? I mean, what's one of the dominant nonlinear control ideas we talked about for the acrobat and cart pole? PFL, but that led to energy shaping. So Goswami did a nice controller based on energy shaping. Right. And he showed that you take your nominal compass gate with its fragile little basin of attraction, which he computed by sampling, pushing the system until it fell down, right? And he showed that with an energy shaping controller, which is derived exactly the same way we derived the other one, so I won't bother. But I can regulate the energy of the system to put me back on the energetic orbit, because this thing is with zero torque, it's passive in the swing phase, so I can just drive myself up to the place where I will passively fall down and hit the right place on my Poincare map. Okay, and that worked locally. That's a good idea. There's another bunch of work that's become popular in our world. Eric Westervelt and Jesse Grizzle and these guys. They talk about hybrid zero dynamics. And more recently, our friend who's going to join the lab is, Shiryev is the advisor in Manchester. These guys have been doing sort of similar work using more optimal control derivations and similar hybrid zero dynamic kind of methods. Let me just cartoon the idea. It's sort of similar to the PFL idea. But these hybrid zero dynamic methods are one of the places where we actually have proofs of convergence. And the way they do it, like in partial feedback linearization, is that when the system is, let me say it carefully here. They find some desired trajectory of the robot, which has a periodic gait that they like. It has actuated joints that follow this trajectory and passive joints that follow this trajectory. If you do a co-located PFL, if you just regulate the dynamics of your system, your actuated joints to follow that trajectory, then the passive one pretty much has to do the same, has to do the right thing. Okay? So the results that these guys on the hybrid zero dynamics, they talk about the zero dynamics of the resulting output dynamics that you drive to zero. Yeah? When your PFL controller has done its job, and it doesn't have to be a PFL controller, it could be a PD controller. When you've driven all your actuated joints to the desired trajectory, if you parameterize that trajectory off, let's say the ankle angle, then your whole big complicated bipedal robot, 5-link, 10-link, whatever, looks like a rimless wheel rolling around the stance foot. And that's a beautiful idea. So maybe the bigger idea here is actually a lot of the walking robots you can think of as having a lot of actuators at all the joints and just missing one just having one passive joint. So a pretty good idea for a walking robot is to just drive all of the actuated joints as a function of the passive joint. And that gives you a dynamical system in one variable. It's a more complicated dynamical system than the rimless wheel. It's one that you can design. But the analysis reverts to basically the rimless wheel type analysis. Okay? So this hybrid zero dynamics is roughly that idea. And then you can sort of do rimless wheel. Yeah?
So, I mean, is this approach like squashing the dynamics, kind of like what you said you didn't like in the first dynamics?
I have had this debate with Eric Westervelt many times. Yeah, I think it is. Yeah, that's a good idea. Just like I say PFL is great, we should use it for a little while until we figure out something better to do. I think they'd admit that too. Their stability guarantees are when you've driven the aerodynamics to zero. You squash the aerodynamics. And you have to have gains that are high enough to squash those arbitrarily fast, right? Now, the bigger idea, I think, is that you can do sort of softer feedback and get some of the same type of performance, but the theory does depend on squashing. So all the stuff I talked about, I think, is sort of the right way to think about walking control. It's a small fraction of what people actually do in the walking robot world. By far, the dominant approach is these Honda Azimuth type robots. Anybody see HRP 4C yesterday? Yeah? What does it look like, yeah? Who saw HRP 4C? Yeah? It looks like a model, yeah? They actually videotaped a Japanese model, walking in high heels, right? And they built one of their newest, it's the AIST robot by Kawada Industries, that it's got now a sort of a female android head on it, yeah? And it walks, I just saw a few videos, but it looks pretty good, right? The shapes are sort of, more feminine, and the gait was a little bit looser, right? But most of the walking robots out there today, most of the successful ones, are all pretty similar to Asimo. And Asimo doesn't do any of this stuff, really. Asimo plays one trick, I could say it sort of in a single line. They try to keep one foot flat on the ground and assume that that foot is bolted to the ground. And they pretend they're a fully actuated system and do trajectory tracking. Yeah? And when they're doing their trajectory tracking, they have to make darn sure that foot doesn't roll off the ground. Right? But if you watch the videos of Asimo, you're going to see it's always got one foot flat on the ground. Running is a small excursion. They just give up on stability for a little bit until they go back to the place where they can catch on the ground. Okay? That's relatively unappealing compared to these, I think, because it uses a ton of energy. I told you in the first lecture, it uses 20 times as much energy as a human when it walks. People have used these type of methods to make a robot that uses the same kind of energy economy as a human. Right? And it's just walking with its foot flat on the ground. It doesn't work on rough terrain. It's not walking as fast as we are. All the energetics of heel strike, you have to do all that with active control because you can't sort of reduce your collision if you're going to land with a flat foot. So this is the better way to do things. Excellent. That's a quick preview into the world of walking. And really, the key message here is it only takes one or two more tools to turn it back into the acrobat problem. Okay? Midterm on Thursday. If you have questions about that, ask John, ask me. If I do disappear, I apologize, but it's for a good reason. And we'll have a good spring break, and I'll see you soon.